Welcome to Ready to Derive. In this video, we're going to be looking at function transformations, in particular shifts, aka translations, stretches, compressions, and reflections. And all of these can be achieved by taking a function and kind of algebraically manipulating it. So if you take that function and add a constant d, or if you add a constant c to x first before putting it into the function, or you multiply by a constant a, or you multiply x by a constant b and plug that into the function. All these lead to different function transformations, which we'll look at one at a time. So by now you must be super excited, so let's get started. So we'll begin by finding what transformation effect we would get by adding a constant d to a function f of x. So for example, let's pretend d is 2, and here's a function for us to work with, and here is a list of the function values for select x values. So we are looking at, let's generate a column that represents f of x plus 2. So we literally just take and say negative 2 plus 2 gets 0, 0 plus 2 is 2, negative 1 plus 2 is 1, 3 plus 2 is 5, 4 plus, and then 3 plus 2 is 5 again. And now we're going to plot these points. But when I say plot the points, that means when x is negative 3, we're going to plot y equals 0. So there. When x is negative 1, y is 2. When x is 0, our y value is 1. So 0, comma 1. When x is 2, it's 5, and 4, it's 5. So I think you can kind of see what's going on here. If we now connect the dots, we see that this has resulted in a vertical, what we call a vertical shift or translation up 2 units. This kind of makes sense. So plus 2, you're just adding 2 to every y value. So then if we were to consider, say, y equals f of x minus 3, we can bypass the table and just know that this is going to result in all the y values going down by 3. So if each of these goes down by 3, let's see, so this point here, 1, 2, 3, and this up here, 1, 2, 3, 1, 2, 3, and then we connect, that results in a vertical shift down 3, as we might have expected. So to summarize that, let's put the little table here. The effect of adding d to the outside of the function is that you get a vertical shift, and it's up if d is positive, as in the green equation, and down if d is negative. And what's really useful actually is to summarize what happens to each individual point. So notice that any point x comma y on the original function, x remains unchanged, and y changes by you add or subtract whatever the constant is. So now we will look at the effect of adding a constant, say c, to x before we apply the function, and what effect that has. So instead of for example, the plus 2 was on the outside of the function in the case before, now the plus 2 is being added inside the function first. So here's our function, and here's our table of values. And this is going to be a little different working this out, because I can't just add anything to f of x. I have to really apply that plus 2 beforehand. So take a couple of examples. Let's look at when x is negative 3. If I plug negative 3 in for x, so I want negative 3 plus 2, which would be f of negative 1. Well, f of negative 1, I can see from the table here, f of negative 1 is equal to 0. And so I could get one data point there. So I know that negative 3 comma 0, negative 3 comma 0 is one particular point on the new graph. But watch what happens when I take the next available value of x. X is negative 1. If I plug that in for x, I still have to add that 2 first before applying the function. I get f of 1, and then if you look, though, the problem is I have f of negative 1, I have f of 0, but I don't have f of 1. So we run into a little bit of an impasse. So we need to kind of go about this more strategically. And the way to do this is to sort of work backwards and think, well, look, I know that f takes on these particular values, negative 2, 0, negative 1, 3, 3. And I need to kind of sort of engineer backwards and think about what must x be to make this happen. Well, I know that if if x plus 2, so if what goes into parentheses is equal to -3, then of course I'll get out -2, because that's kind of what this tells me right here. And similarly, if x plus 2 was to work out to -1, y would be 0. So if I just kind of copy those particular inputs that I need to make this work, then I can kind of work backwards and think, well, what must x be so that x plus 2 is -3? I'm just going to subtract 2. It would have to be -5. And for x plus 2 to be -1, x would have to be -3. And so if you can see that we're just subtracting 2 every time from that input value, subtracting 2. And now I can begin to graph these points. So when x is -5, y is -2. So -5, -2. When x is -3, y is 0. Oh, I already plotted. I figured that point now. There, -2, -1. So -2, -1 would be here. And then 0, 3, 0, 3, and 2, 3. So 2, 3 would be right here. And here we have it. It looks like another shift, but this time it's a horizontal shift to the left 2. So I'll write left 2. So horizontal shift left 2. Now, what happens if, what could we make a determination if we have f of x minus 3? Well, if the one above was left 2, then I'm going to posit the idea that maybe this is taking it to the right 3. So we would then, let's just take every value and move it to the right 3. That means the y values are being unchanged, and the x values are all moving to the right 3. And so we'd get this, and you could kind of make the table in the similar way that I did to kind of prove that, but that results in a shift to the right 3. So let's summarize this. So this is a little kind of the opposite of what you think it should be, right? Because the 3 is negative, but you end up going to the right, and the 2 is positive, and you end up going to the left. So it's kind of the reverse. So this is a horizontal shift, this value of c added in the parentheses, and it's left if c is positive, and it's right if c is negative. And then what does that mean to the, that happens to the point x, y? Well, that means that for every x value, you're going to just do x minus whatever c is. So as we saw that we did here. So this, to get from here, let me just use a different color, to here, we basically just subtracted the x values by 2. And for f of x minus 3, we would just add 3 to all the x values. So now we're going to consider the scenario when we multiply the function by a constant a on the outside of the function. So let's take y equals 2 times f of x. Here's our function again. Here's our table of values. And we can calculate this pretty straightforward. We're just going to take all the y values and multiply by 2 and see what effect that has. So if we graph -3, -4, -1, 0, 0, -2, and then 2, 6, and 4, 6. And if we connect the dots, we can see a kind of distortion, and we call this a vertical stretch of factor 2, because all the y coordinates have been multiplied by 2 and are twice as far from the x-axis as a result. Now, what would we get using the same sort of logic? 1/3 of f of x, we're going to take all the y values and multiply by 1/3. So -2 will go to -2/3, 0 is the same, 0, -1/3, and then these points will, instead of having y coordinates of 3, will both have y coordinates of 1. And again, we have this, what we call a vertical compression. We call it compression because it kind of shrunk vertically, right? So each y coordinate is 1/3 of what it was before. And now we get a sort of bonus situation going on here for a transformation when we introduce a negative number. And to help us with this, I'm going to just erase this, and I think we'll fill these values in. So if we want to look at the effect of -2 times f of x, this becomes 4 0. This will become 2, and this will be -6, -6. We graph these points. What we are going to find, I'm going to just put a dot there because the x-intercepts stay fixed. We have this kind of the same shape, but flipped upside down. So this is a reflection. That negative results in a reflection over the x-axis. So to summarize this, we get vertical stretch if that number in front of f of x, if a is bigger than 1. I put absolute value of a is bigger than 1 just to not get confused with negatives. So if a was 2 or 3/2, we're going to get a stretch. A compression will be when that value, absolute value of a, is less than 1, like a third, half. And then the bonus transformation is a reflection over the x-axis if a is less than 0. This sounds all very complicated, but when we look at the actual effect of the point, so on the point xy, it just goes to x comma ay. Multiplying the y coordinates by a takes care of everything, and you don't really have to worry too much. It's all taken care of in the math. So the final way in which we can affect a transformation of a function is by multiplying x by a constant b and then putting that result into the function. So let's explore what effect that has by looking at f of 2x. So here's our function f of x. Here is the table of values of our key points. And we can't use this table as is, remember, because now we're doing something to x before plugging into the function. So we need the extended table. And I want you to think about this. So instead of writing f of x here, I'm just going to put, so whenever the input is any of these values, then we know that f evaluated at that input are the other values. So if -3 is the input, f of -3 is -2. And now we want our input to be, so let's get, instead of putting input there, we want it to be 2x. So that means that this input column has to correspond to 2x. And then hopefully it's obvious that to get the x values that make those values of 2x, so to get 2x equal -3, you need x to be -1.5. In other words, we have to take this column and divide by 2. So -0.5, 0, 1, 2. Notice the y values stayed the same. So x equals -0.5 generates y equals -2. So let's graph those. -1.5, -2. We have this point, this, and then 1, 3, and 2, 3. And hopefully you can see that all the y values stayed the same, and the only thing that changed was the x values, and that is a horizontal compression of a half. So every point xy, notice it's kind of the opposite of what you think it might be, went to x over 2 comma y stayed the same. So what about y equals f of a half x? It might seem tedious, but I think it would be helpful just to run through this one more time. And this time we're going to say if we want f of a half x to work out to those values, then these inputs have to correspond to half x. And now all we have to do is find x, and the way we would do that is divide each of those by by half, which is the same as multiplying by 2. So let's see what effect this has. That becomes 4, that becomes 8. So if we graph those, -6, -2, -2, 0, 0, 1, and then we have 4, 3, and 8, 3, which is, I guess, a little bit off the graph there. And if we connect those, hope you see that we have a horizontal stretch of factor 2. So even though b is a half, the result is a horizontal stretch of factor 2. So I could write that as 2x, but I'll write x over half comma y. So for our final example, we'll look at just y equals f of -x. We won't complicate it by having a stretch or a shrink in there. We'll just have what is the effect of -x being there. So by the same reasoning, okay, again, just to kind of make sure we got this down pat, we would like to graph f of -x, which means -x has to be these inputs, which means x has to be the opposites of these. And I hope you can sense what's what's coming. So when x equals 3, y equals -2, which is there, and then 1, 0, and then 0, -1 stays the same. And then we have -2, 3, and -4, 3. And what effect that has is a reflection over the y-axis. So to summarize all this, we have, let's summarize it, a horizontal stretch when the absolute value of b is less than 1. So when b was a half, we ended up with a horizontal stretch. But we have a compression, like in this case, when b, the absolute value of b is greater than 1. And then we have a reflection over the y-axis if b is less than 0. And finally, the general rule is that the point xy goes to x over b comma y. So I'd like to end by summarizing what we've learned about transformations thus far. And we'll come at it in a slightly different way, but by putting it in this table, you're going to see some very interesting patterns that help to remember what's going on. So for a shift, if we want to affect a vertical shift or translation, if we recall, all we do is we take the function and then we add a constant d to it. So what does that mean to any point xy? That goes, the only thing that changes is that y is changed by the quantity d. If we want to affect a horizontal translation, if you recall, we had to add that constant to x first before putting that into the function. And what effect did that have on each point? Well, because it's horizontal, y stays the same, and the x coordinates are decreased by the quantity c. So it's kind of the opposite of, as is the case for the vertical shift. Notice that when we're dealing with shifts, it's all about addition or subtraction, unlike when dealing with stretches and compressions. So let's recall. For a vertical stretch or compression, we achieve that by multiplying the function by a constant a. And by the way, compression sometimes is also referred to as a shrink. So if I say stretch, shrink, it means the same thing. And what happened to every point x, y? X stays the same, and the only thing that gets adjusted is y gets multiplied by a. And for horizontal, we do that multiplication, but within the function instead. And so xy goes to, well, what happens to x? It's actually every x coordinate is divided by that quantity b, y stays the same. And finally, a sort of offshoot from if a is less than 0, in this case, we have a reflection over the x-axis. And if b is less than 0, we get an added reflection, but this time over the y-axis. So stretch and compression, what's interesting about stretch and compression, notice it's when you take the function or you take x and you multiply or divide by a quantity. So shifts are kind of rigid transformations. You're adding, subtracting, just moving things around the plane. Stretch and compression, they're distortions, and you achieve that by multiplication or division. Another thing to maybe notice to see is that any vertical transformation happens by you taking a constant and adding it or multiplying it on the outside of the function. So I like to think of this as sometimes referred to vertical changes as it's outside, anything that's happening outside the function. Whereas if in the case of horizontal transformations where y stays the same, the changes are happening within the function. So I write here inside the function. Now, we've looked at each of these in isolation. In the next video, we will look at what to do if all of these are going on at once. How do you process all 4 transformations? Well, 4 and reflections kind of as a subset of stretch compressions. How would you graph something like a f of b of x plus c plus d, interacting all together? Congrats, you made it to the end of my video. Hoping that means you found it helpful, and if so, please do like and subscribe and check out more of my videos on my channel, Ready to Derive.